Great.
Well, this talk actually arose not directly in what we're going to do in VECMA, but more as background to what we've already been doing within IPP on the area of uncertainty quantification. I'm not the expert in this area. Udo von Tresson, who was here up until about 10 o'clock, is the guy who put the talk together. He is at Max Ent, which is just down the road from here. If you have questions, I will try and answer them, but if I can't answer them, I will forward them to Udo and he will try and get back to me. So the idea is to cover what Udo has been doing in the area of uncertainty quantification, the application to more material simulation, sensitivity analysis, and then trying to draw some conclusions from this. This is a fairly generic slide. You could probably apply this to almost anything in uncertainty quantification. There are a range of uncertainties. We have a medium to large number of uncertain inputs, and we have nonlinear interactions between the inputs and the results. And that raises the issue of how good are the results we get from a particular simulation. If we can't quantify the results, then just giving a number is misleading and possibly dishonest. And so part of it is to try and give realistic uncertainties about the answers. The particular example is we've chosen, or he's chosen here, is on the simplest possible model for sputtering. Sputtering is the process where we have incoming atoms hitting a surface and then material from the surface being removed from the surface and make its way out. The BCA stands for binary collision approximation. This is really, we have a bunch of balls inside the material. We have a ball coming in, it hits the balls inside the material, some of them bounce out, and there's a cascade of reactions inside, not so much chemical reactions, just the balls hitting other balls, and we try and keep track of what comes out. Now there are a number of models that have been validated, and two are mentioned there. And what this talk is going to do is try and look at what can we learn about these models. There are uncertain inputs, or probability distribution functions, the composition, the impact angle, what angle the atom or ion is coming in. One of the crucial ones is related to the BCA model, which is what is the surface binding energy. And there are a bunch of other things. But one of the things you notice here is these two models, both of which have been validated, produce quite different answers. And the experimental data is a bit of a mess as well. So what can we do? The basic idea in a lot of uncertainty quantification is to do sampling. The simplest is Monte Carlo, but there are things which, as I will try and show in the talk, do a little better than this. The polynomial chaos expansion is one such method. Again, there's two possibilities of implementation. One is one favored by the physicists and the people with codes, which is a non-intrusive approach. And then the more interesting one for the people who are designing new algorithms or looking at the mathematics is the intrusive approach. And then there's later on possibility of surrogate models. I'm going to start with the sampling and then cover the non-intrusive approach for the spectral expansion. The details I'm going to skip over, partly because I don't know them, and partly because I have a limited slot in which to talk. But the idea is we take a random set of sampling points in our n-dimensional space, do the calculations, and try and draw as much information from them as we can. The approach here is not only to calculate the get the expected value, but also get information about variance and other higher order terms. The advantage of doing it, of calculating essentially this distribution function, is that, as we'll see later, we can get quite a lot out of it, more than we could get from just essentially throwing lots and lots of Monte Carlo simulations. In this particular example, we have effectively reduced the problem to three uncertain quantities. The unknown, or the energy of the projectile coming in with some uncertainty associated with that. The binding energy, which is nominally this number, but is assumed to be uncertain within some range. And an angle, which again is uncertain within some range. And the range is given here, essentially. And what we're interested in is the sputter yield of the quantities coming out, and also a measure of the uncertainty in that quantity. So effectively we have distribution function of inputs, and what we're interested in then is what is the distribution function of the output. As a first example, we essentially just do a sampling within the space. In this case, we only have 3 inputs, so we can afford to do this. It is 20 cubed in this particular example, and we just get this number as an output. The actual value is not that critical, but we come back to a comparison of this number with a more detailed approach. If we're looking at the distribution of samples, we have an energy impact angle in this, and then color-coded in that is the sputter yield. The disadvantage of working in this number of dimensions is it's almost impossible for the human to really make any interpretation of that. Moving on, if we do a spectral expansion, so we're now making some assumptions about how we can expand the thing. We build essentially something in a Hilbert space. We build it on the basis of a orthonormal basis. We calculate, or we're going to calculate coefficients and the basis functions. Depending on what your type of variable is, you have different choices of weight functions and orthogonal polynomials, and also of the basis. In this particular case, we are using Gaussian approximation. We're going to be doing expansion in terms of Leibniz polynomials. As I indicated here, there are other options available. I mentioned earlier that intrusive methods are possible, but in this case we're going to be looking at non-intrusive methods. The advantage of intrusive methods is that in principle you solve the problem once and you have all the information you need. The disadvantage is that if you had the original code, you're going to have to maybe not throw it away, but in some cases throw it away and rewrite a new code from scratch. And for some problems you can do this, but for more complicated cases where you might have 50,000 or 500,000 lines of code, the incentive to throw it away and start from scratch is somewhat limited. The advantages I've already mentioned is you don't have to reformulate the governing equations. We're going to build we're going to try and find these coefficients by essentially looking at running the code, the original code, at particular points. The quadrature rule that we're going to be needing is in general on some sort of sparse grid, or some sort of grid, but there are ways of essentially making it more sparse so that we don't have quite so many calculations. Effectively, this is just showing that we are going to be able to calculate a mean and a variance, and once we have done this work, we will have no need for further simulations for any additional quantities, as we will see later. The advantage is that we can build on this to calculate other quantities if we get any in terms of the calculation, this is the new grid on which the calculation was done. This is just a reminder of what we got previously. Based on calculating moments of the output from this, we come up with a new estimate of the yield with an uncertainty. These are very, very similar. But what is important here is that in this case we needed 1/40th of the compute time for this calculation. Now, in the case of the BCA, this is not quite so critical. It's a relatively fast calculation. But if you have more complicated models, being able to reduce the number of times you have to calculate the original quantity by a factor of 40 or more is critical. We can calculate the sensitivity to the input values. This is essentially the analysis of Sobol. What is important? Okay, this is essentially the mean, the univariate expansion, and then the bivariate. We can take it further. What is critical in this particular analysis is that once we have that polynomial chaos expansion that we did earlier, we don't need to do any more calculations because we can calculate these Sobol indices directly from the information we already have. And that saves a significant amount of analysis. Applying this to the example that we had, we find that almost all of the uncertainty in the results can be explained in terms of these expansion in terms of the univariate functions. If we go to the bivariate, it's less than 0.01. And in particular, the largest uncertain, or the quantity that has the biggest impact on the answers, is this binding energy at the surface. That then provoked Udo to look at, can we quantify this binding energy better by comparison of the code results with particular measurements. And in this particular case, the idea was to redo measurements for 4 different angles at a particular energy, and then apply the UQ methods to try and calculate that. And then in doing that, the most probable value of ESP, which originally we had was 4.2, shifts to somewhat higher energies, 4.8, and then we can look at how this would change the graph I showed you earlier. When we do that, the trim calculations move from the red points down to the green points, which somewhat better describe over the whole the experimental data. The other conclusion in this analysis is that the S-trim model can almost certainly be ruled out. The better idea of these, applying the measured uncertainties in the code, sorry, the uncertainties that the code gave you, and the experimental measurements effectively says this is not a description of the underlying data. Quite where the problem is a bit of a problem because the source is not really released of this code. It's a black box. And not too surprisingly from the group, they would prefer that people use this code, which happens to be open or semi-open source and comes from that same group, from predecessors of that group. Once we have this, just further things, we can, using the polynomial chaos expansion, calculate the gradients if we need to optimize things. We don't need further adjoint models. If necessary, you can also build the Hessian. The limitations, and there always are limitations, is that as your problem size in terms of the number of inputs grows, your number of integrals is going to grow quite strongly. But I've already mentioned sparse integration techniques can help you with that. Another issue is that the basic approach here is not adaptive in that if you build it as a whole, you don't zoom in on the regions where things are surprising. To summarize, uncertainty quantification in terms of the polynomial case expansion offers a non-intrusive method that is general purpose. It's optimized in the selection of the simulation points. The influence of input parameters combinations is byproduct, so essentially working out what the sensitivities to the inputs are, and that model gradients are accessible. Udo feels that it's suited for a medium number of uncertain parameters, and you can get away with 100 to 1,000 simulation runs, which in some cases is certainly feasible, in other cases it's starting to become marginal. I'm sure we each think of cases where this would work, and there's other cases where we wouldn't expect it to work. It can provide access to otherwise inaccessible quantities. It has its limitations. If you have a phase transition in the phase space, then this is not really going to work. What you really want is something that is relatively smooth over the whole domain in terms of how things behave. And with that, I would like to thank you for your patient attendance and ask if there are any questions.